going through what we did last week. So we mainly discussed the concepts of the principal stress, and we discussed the concept of the stress itself. We said that the stress is actually not like a vector, not like a scalar, it's kind of a tensor, this complex type of behavior, which is where we are going to discuss to some length today, the concept of the tensor. And we said why this is relevant. And then I've had a general introduction for the course and the material we have in this course. So today is going to be the first introduction into the continuum mechanics. And I'm going to cover the concept of the tensor in general. So this would be the main focus of the lecture today. I'm going to introduce you to some notation as well. And this is basically what we are going to discuss mainly today. Okay. First of all, the concept of the continuum mechanics. I mean, continuum mechanics start from the assumption that any material we have is basically a homogeneous type of material. So if you take any type of material, steel, for example, and then you divide it into smaller and smaller parts, you can keep dividing it without losing the properties of the steel. I mean, no matter how refined you go into your splitting, no matter how small particles you get, you are always going to have particles of steel. And these particles will have exactly the same properties of the steel, so they will not lose their properties. And whatever field property, or whatever field properties you assign to steel, you can assign to these parts. Assuming, for example, you have a piece of steel that is moving at a specific speed, then these particles, all of them will be moving exactly at the same speed. And then if we're talking about the temperature, this will still apply to them. If we talk about acceleration, it will still be applied to them. Now, what do you think about this sort of concept? Do you think this is a realistic concept? Or this is a realistic description of the material? Now, think about steel. Let us forget about concrete. Now, of course, if you split concrete into smaller and smaller parts, you are going to lose the properties of the concrete. I mean, if you have a piece of aggregate, it's not going to be the same like cement. It is not going to be the same like an air bubble inside the concrete. So this is going to be different material properties, obviously. Now, how about steel then? Would you still think that this would work? Just for the sake of argument, let us assume that you have a very perfectly homogeneous piece of steel. And this piece of steel is really can really have pretty much exactly the same properties everywhere within this piece of material. Would this concept of continuum mechanics still be meaningful? Let us talk about a situation where we're talking about an elastic piece of material. Would this be correct? It is going to be correct up to a certain scale. Then beyond that, you know that material is basically formed from atoms and molecules. So it is not going to work on the scale once we get into the molecular scale of the material. Now, if we get into that level, this is going to, the continuum mechanics would not work. And what is going to work there is going to be the quantum mechanics. So quantum mechanics would work on this scale, but for a larger scale, is going to be the continuum mechanics. Now, the continuum mechanics would work for under certain set of assumptions. As I said, for example, if we're talking about relatively larger scales, but it will fail to describe the behavior of material once we get into really small scale. So continuum mechanics, for example, is not going to work for nano material. So if we're talking about nanotechnology, continuum mechanics would not be very, very good at describing the behavior, and we are going to need something else. So this is a situation, for example, where continuum mechanics is not going to work. Now, in general, for structural engineering, again, for probably the majority of you are going to work under the assumptions that are valid for continuum mechanics. But I want you to remember that this is going to describe a specific range of material at a specific range of scales. Okay? Now, this is the first thing I want to introduce about continuum mechanics. And I mean, it doesn't describe everything correctly, but it basically works for us in structural engineering and civil engineering. It works really well, and this is why we have been using it for the past 200 years. Now, other than this, I want to tell you also one more thing. Probably you would know that. If you don't, I want to bring it to your attention that in physics in general and in mechanics specifically, we have two types of laws. We have the conservation laws and we have the constitutive laws. The conservation laws, they are universally valid and they are correct because they describe conservation of material, conservation of energy. These type of laws, they are fundamentally correct. I mean, nobody can argue about the conservation of energy, not nowadays. Now, if you get into the constitutive laws, for example, the relations between stress and strain, these type of laws describe phenomena using some mathematical equations, but these equations are based mainly on the observation. So they are correct because we have observed that they work for us. But in the reality, it might be the case that in some scenarios they would not work. So they are purely based on observation, some mathematical equations expressing some observations we are making. Now, as I said, the conservation laws, they are physically and mathematically and logically correct, but the constitutive laws and the vast majority of the discussion we are going to have in continuum mechanics in this course are going to cover constitutive laws. And these laws, as I said, they are correct based on observation. If we make different observations, they may fail. All right, so this is also I want you to remember. Now, this is the two things which I want to introduce you into before getting into the continuum mechanics. And then I'm going to discuss basic tools that we are going to need to work on the topics we are going to discuss in this course. So the first thing we need to describe quantities that are independent on the observer. So I'm going to probably discuss this a little bit at length. Now, let us assume that we have a space that you are interested in studying, and we have some coordinate system. I'm going to call it X, Y, and Z, or probably instead of using X, Y, and Z, I'm going to use some numbers for the coordinates. So I'm going to call it X1, X2, and X3. Now, from this point onward, I'm not going to use X, Y, and Z. I'm going to use X1, X2, and X3, which is pretty much the same thing. Now, assume that you are interested in the temperature at one point. So let us say that this is one point, and you want to measure the temperature at this point. Now, this temperature at this point, where you have specific coordinates for that, so let us assume that this is the coordinate X1, X2, and X3, you have one number for the temperature. Now, this number is independent of on the observer. And for example, instead of using this coordinate system, if you move into this coordinate system here, so this is X bar, X2 bar, and X3 bar. For example, if you move into this coordinate system, where under the new coordinate system, you have X1, X2, and X3, all in bars, the temperature would always be the same, right? Now, if we're talking about the density, for example, this is also correct. If we're talking about the humidity would also be the same. Now, these sort of parameters, which will be intrinsically independent on the observer, these type of parameters, they are scalars. And in this course, we are going to refer to them using probably the Greek letters. So, for example, for the temperature, we can use theta. For the density, we can use gamma, and so on. So this is the first quantity that we are going to need. It's going to be a scalar, all right? Now, you also know that there exists some quantities that not just involve a magnitude, it involves also a direction. So let us, for example, take the force F. and we want to describe it using a coordinate system x1, x2, and x3. And in fact, let us simplify this. And to start with, let us assume that we are talking about a two-dimensional coordinate system. Let us take f in a two-dimensional space. Let us assume that f is actually happening in a plane. So this is x1 and this is x2. Now to describe it in this plane, we just take the components of this force. So this is, I'm going to call it fx1, and then you have the component in the x2 direction. So this is the length there, and this is fx2. And you can write it in this way. F is a vector of fx1 and fx2. Now, this can be positive or negative, or can be different things based on whatever direction you have for this vector. Okay, so these components can change based on the vector, but also based on the coordinate system. Now let us assume that we change the coordinate system. Instead of using x1 and x2, I'm just going to use another one. I'm going to call it x1 bar and x2 bar. Now, if you want to project this vector in this coordinate system, you will find these components to be fx. I probably just write it down. So this length here is fx1 bar, and the x2 bar is very small. And it's probably just this length there is fx2 bar. So in this case, the same vector written in the different coordinate system is going to be fx1 bar and fx2 bar. Now, in the general case, this number would be different than this one, and this one will be different than this one. In the most general case, this is going to be different numbers in there. However, the intensity of this vector, this is f and this is f. So the intensity of this vector, the magnitude of this vector would always be the same. So to find out the magnitude of this vector, you just take the square root of the sum of the squares. So the magnitude of this vector is going to be the square root of the sum of the squares. So it is fx1 squared added to fx2 squared. This is equal to fx1 bar squared added to fx2 bar squared. So the magnitude of this vector is the same, and the vector actually is the same. It is just that direction, it is just that the direction of the coordinate system or the location of the coordinate system is changing between one coordinate system and another coordinate system. Now, let us move into 3 dimensions, and let us assume that this vector exists in a 3-dimensional space. Now, if this vector here, f, exists in a 3-dimensional space, x1, x2, and x3, then in this case, the components are going to be fx1, fx2, and fx3. So you have one extra component. Now change the coordinate system, x1 bar, x2 bar, x3 bar, you will get different components there. Again, it is going still to be the same vector. You check the magnitude is the same, and actually you are describing the same vector. It was just a different projection for this vector. This is the whole thing that you have changed. All right, are you clear about vectors? Now I'm going to move into something slightly more complex. There exist quantities. When you talk about vectors, probably you can think about forces. Forces, pressure, something that would have a unified direction that is happening only in one direction, it would active in one direction. Now there exist the quantities that are active in multiple directions at the same time. Now, stress is an example for that. So let us take a coordinate system again, x1 and x2. I'm going to start from 2 dimensions because this is the simplest way to project it. And let us project it into this Cartesian coordinate system. Now, to project it, you cannot project it into components like we just did for a force. To project it, you need to have some sort of a square. I mean, you probably have seen this square, and then you can project this physical quantity into directions. Now, the stress will be active, as you know, in this direction, which we call it a shear stress. I'm going to call it sigma 1, 2, or sigma 2, 1. It's the same here, 1, 2, and sigma 2, 1. And then you have normal components. I'm just going to use a different component for the normal component. I'm going to call this one sigma 1, 1, sigma 2, 2, sigma 1, 1, sigma 2, 2. And if you project this, you cannot write it in a vector. You need to write it in a matrix form. So the matrix would be sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2. All right, see, I have moved from a quantity that has one direction in 2D or 3D into a quantity that has multiple directions. Now, it is not just one, it's multiple. The stress is active in multiple directions all at the same time. So this is the difference between the force and the stress. Now let us change the coordinate system. Instead of using x1 and x2, let us move back to this x1 bar and x2 bar. Now, the projection of the stress will now need to happen on this square here. I'm just going to draw the square. And not to confuse you, probably I'm just going to draw the square on top of the old one. So to project it, you will see that some part of this component and some part of this component are going to move in the vertical direction or in the normal direction, and some of this component and some of this component is going to be active in the shear direction. The same is going to happen here and here, here, and here, here, and here. Now, if you write it in the new coordinate system, you'll see that this is sigma 1, 1 bar, sigma 1, 2 bar, sigma 2, 1 bar, and sigma 2, 2 bar. Now, this number is not the same like this number, and this one is going to be different than this one. However, this quantity here is the same. This one and this one is exactly the same. Now, how do you know that they are the same? We said that for a vector, you can calculate the length of this vector, the amplitude of this force. But for the stress, you cannot calculate the intensity of the stress or the magnitude of the stress. For the stress, you calculate the eigennumbers. I'm going to come to the eigennumbers at the end of this lecture. The eigennumbers would basically express something comparable to the intensity of the force or the strength or the magnitude or the volume of the force. All right, now this is the case in 2D. However, you can work exactly the same situation in 3D, and actually the stress would be most of the time would be active in 3D, unless we talk about the plane stress situation, which is an approximation of the reality. But if you move into 3 dimensions, you have x1, x2, and x3. In this case, the projection would happen on a cube. And you have probably seen this cube where you have the normal stresses, and then you have the shear stresses in one direction, the shear stresses in the second direction. And in this case, you can project it into sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, 2, 2, and 2, 3, sigma 3, 1, 3, 2, and sigma 3, 3. Now you change the coordinate system. Instead of this one, you use another one. You have x1 bar, x2 bar, and x3 bar. This is going to change, and you are going to have the bars in there. Again, sigma 1, 1 is not exactly the same number as sigma 1, 1 bar, and sigma 1, 2 bar is different than sigma 1, 2. However, the stress tensor would always be the same. So the stress as a phenomena is always going to be the same stress. Okay, so this is something really important I want you to remember. And this case is comparable to the vector in 3 dimensions. All right, so this is, this type of this discussion which I've just had is probably the most important discussion I'm going to have today, but this is the most important points for you to understand. So do you follow what I've explained here? Do you have any questions related to this? All right, so in this case, I'm going to introduce you into the name of this quantity. Now, this is a physical quantity you call a scalar. This is we call a scalar. This one here we call a vector. This is a vector, and this is a vector. And this one here, it has a name. The name is tensor. In fact, tensor is the most general name for all these quantities we have discussed, tensors. So it is the name for this one, and for this one, and for this one. Now, these ones here, we call them zero order tensor. These ones here, we call them first order tensors. And these ones here, we call them second order tensors. All right. Now, for this course, for just specifically for this course, we are going to stick with the names we have introduced at the beginning. So I'm just going to call these quantities scalar, these quantities vector, and this quantity here is a tensor. All right. Now, tensor, as I said, is the name for all of them. It's just different orders of tensors. However, in this class, we are going to keep the name tensor for the quantities that second order tensors, and first order tensors are going to be called vector. First zero order tensors are going to be called scalar. And I want you also to know that there exist also quantities that are represented in third order tensors and fourth order tensors. And in physics, in general, I think we have quantities up to our meaningful quantities up to fourth order tensors. Fourth order tensors, they serve specific purpose in physics, the physics we know today. However, in math, you can have any number of orders. Think about it, just like if you want to describe a vector in 4 dimensions. So you have the vector to have the components F1, F2, F3, F4. Now, this is a vector in 4 dimensions, which does not have any physical application. But in math, this is something that exists. Also in math, there exist tensors of the first, second, third, fourth, fifth, 7th, 10th, 20th order. All right. So just for the purpose of this course, we are going to restrict ourselves to 3 dimensions and second order tensors. So for this course, we are going to work in 1 or 2 dimensions. Usually I'm going to use the 2 dimensions just for you to simplify something, and then we move into 3 dimensions. So we are going to restrict our case to 3 dimensions, and then the maximum order tensor we are going to have is the second order tensors. Okay, which looks like matrices. So sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, 2, 2, 2, 3, 3, 2, and 3, 3. x1 and x3 we moved into x1 and x2 bar. All right. See, in this case, the components here would be different numbers. However, the stress does not change, all right? This is just a projection. I mean, we're talking exactly about the same thing that is happening here when we talk about vectors. When you change the coordinate system from this one to this one, you are still talking about the exact same force. Now, you noticed, of course, you've noticed some change in x1 and x1 bar. However, we're still talking about the exact same vector. Now, stress, the stress itself as a physical quantity would have exactly the same behavior. You have a specific coordinate system, you can project it into this coordinate system. You have a different coordinate system, you can project it into the new coordinate system, but the magnitude of the stress is exactly the same. Now, I said before, for a vector, you just calculate the length of this vector. If it is force, then it is the magnitude of this force. For stresses, since we're talking matrices here, is still relevant. There is specific properties for this matrix are going to be exactly the same like this one. So these two matrices would have exactly the same properties, which would reflect the fact that they are representing the same stress. But the numbers you can see in there are going to be slightly different. Okay. I'm going now to talk a little bit about the representations, basically how we write them down. We have a coordinate system, x1, x2, and x3. In any coordinate system, you have a unit vector. So basically, you have a vector that has a length, or probably just before we get into the unit vector, E1, E2, and E3. Before we get into the unit vector, you have the vector F. You already know that this can be written just like a vector, like a column matrix is F1, F2, and F3. So this is the first representation, but you can also write it as a summation of the basis vectors. So the basis vector are small vectors. The vector E1 is a unit vector pointing in the x1 direction. E2 is a unit vector pointing in the x2 direction, and E3 is a unit vector pointing in the x3 direction. So you basically write this vector here. And by the way, I'm using this bar to refer to the fact that this is a vector, all right? I mean, some people would refer to the vectors with an arrow. In mathematics, I'm used to is to use a bar in there. So this would be then F1 multiplied by E1 added to F2 multiplied by E2 and F3 multiplied by E3. So you are just saying that the projection of F on the x1 direction is a vector of the magnitude F1. The projection of F in the x2 direction is a vector of the magnitude F2, and so on for F3. So this is a direction, and this is a magnitude. Now, this one and this one are representations for the exact same vector. So you can choose to write it as a matrix, as a vector, or just to use it, write it in terms of the basis vector. So you can write it either in this way or in this way. Now, this is easier, and the majority of the applications I'm going to discuss, the majority of the examples, I'm going to use this sort of representations. But if you look into continuum mechanics book, usually they would write this, they would write vectors in this form. I'm going to tell you in a minute why this would be useful in continuum mechanics books. Now, the same is also correct if you look into the tensors. So for sigma, you have sigma 1, sigma 2, sigma 1, 3, 2, 1, 2, 2, and 2, 3, 3, 1, 3, 2, and 3, 3. So this expression here is equivalent to this one here. And again, I just should be using bar here to express this as a tensor. And you can also write it in this format. Now, writing it in this format is slightly lengthy, but I'm just going to show it to you just once. So this can be written as E1 sigma 1, 1, E1 added to sigma, or probably just E1 sigma E2. This is 1, 2 added to sigma, E1 sigma 1, 3 E3, and so on. So you basically add a summation if you want, where each quantity is an expression that is active in two directions. Now, this is active basically in two directions because it has two indices. And if you think about the projection about this square, x1 and x2, you'll see that sigma 1, 1 is actually happening in the one direction and active on this plane. This plane is identified by the normal direction to it. So this is sigma 1, 1. And it kind of has two directions. I mean, it's difficult to think about it, but the quantity, the physical quantity behaves in this way. Okay, so each one of these components here will have two directions associated to it. In the case of sigma 1, 1, it is E1 and E1. In the case of 1, 2, it is E1 and E2. And so on for sigma 1, 3 is 1 and 3. So every single component is associated with two directions, it's not one direction. So this is why the behavior of tensor is more complex than the behavior of vectors, because every component of a vector is associated to one direction, whereas for the tensors, every component is associated to two directions. Now, if you want to figure out which component of a vector is associated to E1, again, I'll probably just, we have this vector here. Sorry, I should use black. You have this vector here, F is equal to F1, F2, and F3. And you want to find out which components of this vector is related to E1. Now, E1 can be written as 1, 0, 0, because we know that E1 is a unit vector for the x1 direction. The magnitude of E is a unit vector, so the magnitude is 1, and it has no projection in the x2 and x3 direction. So this is how the E1 is written. Now, you can find which component is related by multiplying F with E1. So multiply them using the dot product. In this case, F1, F2, and F3 is multiplied by 1, 0, and 0. And this is multiplied by this is multiplied by this is multiplied by this, and the final product is going to be F1. So F1 is the component that is associated to E1. Now, if you want to find the component of the stress, which is associated to the direction, which is sigma 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3, 3, 1, 3, 2, and 3, 3. If you want to find which component is associated to E1 and E1, as I said, because you have two components in there, you multiply it by E1 from left and from right. So I'm just going to multiply it by E1 from left. This is 1, 0, 0, and 1, 0, 0. And in this case, I'll just remove this here. Sigma 1, 1 multiplied by 1, sigma 1, 2 multiplied by 0, sigma 1, 3 multiplied by 0, and the summation will be written here. So it is sigma 1, 1 added to 0, added to 0, it is sigma 1, 1. Sigma 1, 2 added to 0, added to 0 is sigma 1, 2. And sigma 1, 3 added to 0 and added to 0 is sigma 1, 3. This is just a matrix vector multiplication. Now, you need to multiply this one with this one. So you have 1 multiplied by sigma 1, 1, 0 multiplied by sigma 1, 2, and 0 multiplied by sigma 1, 3. So this is going to be sigma 1, 1, and sigma 1, 1 is the one associated with the vector E1 and E1. Just like we identified at the beginning.